Okay, hello everyone. Let us continue the second part of today's class. Okay, in the first part, we have talked to here. If the vectors are not linearly separable, learning will never reach a point where all vectors are classified properly. The most famous example of the perceptron's inability to solve problems with linearly non-separable vector is the Boolean exclusive OR problem. The solution spaces of decision boundaries for all binary functions and learning behaviors are studied in the reference 170. Okay, let us see reference 170. Okay, reference 170, okay, is a book written by Leo, and Leo. Okay, so the title of the book is Learning Behaviors of Perceptron. The publisher is the iConcept Press in 2013. Okay, let us go back to the place where the here. So in the context of neural networks, a perceptron is an artificial neuron using the Heaviside step function. Okay, we will introduce what is Heaviside step function later as the activation function. The perceptron algorithm is also termed the single-layer perceptron. To distinguish it from a multi-layer perceptron, which is a misnomer, okay, we will introduce what is multi-layer perceptron and what is the meaning of the word misnomer later. Okay, which is a misnomer for a more complicated neural network. As a linear classifier, the single-layer perceptron is the simplest feed-forward neural network. Okay, I will introduce what is the feed-forward neural network later. Okay, next let us introduce the learning algorithm of the perceptron. Below is an example of a learning algorithm for a single-layer perceptron. For multi-layer perceptrons where a hidden layer exists, more sophisticated algorithms such as backpropagation. Okay, I will introduce what is backpropagation later. Okay, backpropagation is a very important algorithm when training the neural network. Okay, backpropagation must be used if the activation function or the underlying process being modeled by the perceptron is nonlinear. Alternative learning algorithms such as the delta rule, okay, I will introduce what is the delta rule later, can be used as long as the activation function is differentiable. Okay, I think you have already known what is a differentiable function because you have taken the course calculus. Okay, nonetheless, okay, I will explain the meaning of the word nonetheless later. The learning algorithm described in the steps below will often work even for multi-layer perceptrons with nonlinear activation functions. When multiple perceptrons are combined in an artificial neural network, each output neuron operates independently of all the others. Thus, learning each output can be considered in isolation. Okay, definitions. We first define some variables. Okay, first, R is the learning rate of the perceptron. Okay, we have introduced what is the learning rate before. If you forget, you can search for learning rate in this handout. Okay, and you can see on page 40, problem 1, what is the learning rate, and you can review the solution. Okay, so let us go back to the learning rate. Okay, here. Okay, so R is the learning rate of the perceptron. Learning rate is between 0 and 1. Larger values make the weight change more volatile. Okay, what is the meaning of the word volatile? Okay, I will explain it later. Y is equal to f of z denotes the output from the perceptron for an input vector z. Capital D is equal to x1 d1 to xs ds is the training set of S samples, where xj is the n-dimensional input vector, and dj is the desired output value of the perceptron for that input. We show the values of the features as follows. Okay, xji is the value of the ith feature of the jth training input vector, and xj0 is equal to 1. To represent the weights, wi, okay, you can see that w denotes the first letter of the word weight. Okay, wi is the ith value in the weight vector to be multiplied by the value of the ith input feature. Excuse me. Okay, because xj0 is equal to 1, the w0 is effectively a bias that we use instead of the bias constant b. Okay. So to show the time dependence of w, we use, where w is the weighted vector. Wi of t is the weight I at time t. Okay. Next, we introduce the steps of the learning algorithm. The first step is to initialize the weights. Weights may be initialized to 0 or to a small random value. In the example below, we use 0. Okay, and for the second step, for each example j in our training set, capital D, perform the following steps over the input xj and desired output dj. Okay. So step 2a, calculate the actual output. So yj of t is equal to f of w of t dot xj, and is equal to f of w0 of t times xj0 plus w1 of t times xj1 plus w2 of t times xj2 plus so and so on plus wn of t times xjn. Okay, so step 2b, update the weights. wi of t plus 1 is equal to wi of t plus r dot dj minus yj of t, okay, times xji. Okay, for all features 0 is smaller than or equal to I, and I is smaller than or equal to n. R is the learning rate. Okay, we have search for learning rate. Okay, you can search the meaning of the learning rate in this handout. Okay, step 3. For offline learning, the second step. Okay, let us see the second step. Okay, here is the second step. Okay, may be repeated until the iteration error 1 over s times summation j is equal to 1 to s, and the absolute value of dj minus yj of t is less than a user specified error threshold gamma, or a predetermined number of iterations have been completed, where s is again the size of the sample set. The algorithm updates the weights after steps 2a and 2b. Okay, let us see steps 2a and 2b. Okay, this is step 2a. Okay, here. And this is step 2b. Okay, here. We have introduced them. Okay, these weights are immediately applied to a pair in the training set and subsequently updated, rather than waiting until all pairs in the training set have undergone. Okay, I will explain the meaning of the word undergone later. These steps. Okay, next let us see two figures. Okay, so first is this figure. Okay, so this is figure 36, a diagram showing a perceptron updating its linear boundary. Small training examples are added. Okay, there are 4 subfigures in this figure. So let us see subfigure 1. Okay, the x-axis is the domestication. Okay, what is the meaning of domestication? Okay, domestication is the process of bringing animals or plants under human control in order to provide food, power, or company. Okay. So, and the y-axis is the size. Okay. So in the beginning we have a sample. You can see that it is a dog, and it is a cat, and it is the boundary. Okay, to separate cat and dog. Okay, next in subfigure 2 we add another data sample, which is another dog. Okay, so there is another sample point here. So the linear boundary has been changed to this. Okay, in subfigure 3, we add another two samples. Okay, this dog and this cat. Okay, so the linear boundary changes again to this line. Okay, finally in the subfigure 4, we add another sample, which is a dog. Okay, so the linear boundary changes again to this line. Okay, next let us see figure 37. The appropriate weights are applied to the inputs, and the resulting weighted sum passed to a function that produces the output O. Okay, let us see this figure. Okay, this is a perceptron. Okay, and there are inputs I1, I2 to IN. Okay, totally N inputs. And we calculate I1 times W1, I2 times W2, and IN times WN. Okay, where W1, W2, and WN are weights. And then we add them up. Okay, use the add operation and pass the result through a function f, and the output of the function f is the output O. Okay, so if we represent it in one equation, O is equal to f of summation k is equal to 1 to n ik times wk. Okay, next let us see the convergence issue of the perceptron. Okay, when designing an algorithm, the convergence is very important. Okay, because we need to know under what condition does the algorithm converge or diverge. And we also must also to study the speed of the convergence. Okay, so if an algorithm converges too slowly, okay, then the algorithm is not useful. Okay, convergence. The perceptron is a linear classifier. Therefore, it will never get to the state with all the input vectors classified correctly if the training set D is not linearly separable. Okay, I will introduce what is the meaning of linear separable later. Okay, that is, if the positive examples cannot be separated from the negative examples by a hyperplane. In this case, no approximate solution will be gradually approached under the standard learning algorithm, but instead learning will fail completely. Hence, if linear separability of the training set is non-a priori, okay, what is the meaning of a priori? Okay, it means in advance. Okay, so one of the training variants below should be used. Okay. Okay, if the training set is linearly separable, then the perceptron is guaranteed to converge. Furthermore, there is an upper bound on the number of times the perceptron will adjust its weights during the training. Suppose that the input vectors from the two classes can be separated by a hyperplane with a margin gamma. Okay, that is, there exists a weight vector W where the norm of W is equal to 1. Okay, the norm of W is the length of the vector W. and a bias term be such that W dot Xj is greater than gamma for all j with dj is equal to 1. Okay, do you remember what is dj? Okay, let us review it. Okay, here dj is the desired output value of the perceptron for that input. Okay. So, and W dot Xj is smaller than negative gamma for all j with dj is equal to 0, where dj is the desired output value of the perceptron for input j. Also, let capital R denote the maximum norm of an input vector. Novikov in 1962 proved that in this case, the perceptron algorithms converges after making big O of capital R square over gamma square updates. Okay, I think you know that a big O is a method, is a measure, okay, to evaluate the complexity of an algorithm. Okay, usually the time complexity. Okay, the idea of the proof is that the weight vector is always adjusted by a bounded amount in a direction with which it has a negative dot product, and thus can be bounded above by big O of the square root of t, where t is the number of changes to the weight vector. Okay. Okay, however, it can also be bounded below by big O of t, because if there exists an unknown satisfactory weight vector, then every change makes progress in this unknown direction by a positive amount that depends only on the input vector. Okay. Okay, next. While the perceptron algorithm is guaranteed to converge on some solution in the case of a linearly separable training set, it may still pick any solution, and problems may admit many solutions of varying quality. The perceptron of optimal stability, nowadays better known as the linear support vector machine. Okay, so usually the support vector machine, okay, if translated into Chinese, is 支援向量机. Okay, and the abbreviation of support vector machine is SVM. Okay, was designed to solve this problem. Okay, please see Krauss and Mazur in 1987. Okay, so we have briefly introduced what is the perceptron. Okay, so next we are going to look at problem 2. What is a multi-layer perceptron? MLP. Okay, the proper noun that appears in our slides. Okay, solution. A multi-layer perceptron MLP is a fully connected class of feed-forward artificial neural network ANN. Okay, we will introduce what is the meaning of feed-forward later. The term MLP is used ambiguously sometimes loosely to mean any feed forward ANN. Okay, it is 25 minutes. Okay, let us take a break.